welcome to the second day of our Meet the Academics. Today we have Nick Chilton, who's going to be giving you all a talk on theoretical chemistry. And at the end, it will be followed by a short question and answer session. So this event is hosted by the University of Manchester ChemSoc and PAS. If you have any questions, please type them in the chat during the talk or during the Q&A session, and one of us will read them out for you. So now I'll hand you over to Nick, who's looking forward to giving you all an insight into his research.
Great, thanks very much, folks. So yeah, it's a pleasure to be here. Really delighted to have the opportunity to speak to you all this afternoon. Now we are past midday, there we go. So thank you for coming along. Happy to answer any questions, whether they're about research or life and the meaning of it and how we get out of this pandemic. I don't think I can cover that one, but happy to chat for whatever you want. So let's I'll just load up this talk and then we can go from there. So this should all be functioning. Can you all see that okay?
Yeah, that's great.
Perfect. So I've got the little laser pointer, so hopefully that's going to work for us all. Okay, so yeah, as the introduction said, my background is in theoretical chemistry, and I have a particular research interest in molecular magnetism. Now, I think Dave Mills gave a talk yesterday, so if any of you were at that session, I'm sure he gave you a bit of an overview of the chemistry aspect of things, and hopefully I can complement that with a bit more on the theory side of things, because we work quite closely together these days on our work. So of course I work at the University of Manchester, and it looks something like this, and hopefully when I get back there it might look like this again, but it won't be hopefully long before we're all back in without a problem. Okay, change slides, won't come and do that. There we go. Okay, so who am I? I came from Melbourne, Australia. You might be able to tell with my accent, you might not. And after I finished high school, I had a bit of a question. I was quite interested in amateur theatre at the time, and so was I going to do a degree in music theatre or was it going to be science? And I ended up doing science because I thought that would probably be more likely to give me a job at the end of it, despite loving musical theatre. Anyway, I didn't think I was going to be an academic. I just liked science and thought I'd give it a go. So after high school, I went to Monash University in Melbourne to do my chem degree. I then did an honours degree in chemistry, which is just like an integrated master's, so it was a 4-year degree in total. I stayed on to do a year as a research assistant at Monash before I moved to Manchester to do my PhD, after which I spent a year as a postdoc in the EPR facility, also at Manchester, before starting my independent research career in 2016. As a Ramsay Fellow, and then I got a Presidential Fellowship in 2018, and then last year I started a Royal Society Fellowship. So lots of different things, and happy to answer any questions you might have about what this all means, and if you're interested in going down this academic route. Right, but it's not really important who I am. The more important thing is the research group, right? These people, these fantastic, interesting, fun bunch of people, clever, insightful, creative people are the ones doing most of the research. I'm there helping and writing and thinking, but these are the ones at the coalface. So mainly thanks to all these people. Why does it keep doing that? Okay, so what's theoretical chemistry? I'll give you a bit of an overview of what it's all about first, and then I'll talk a bit about my research. So chemistry, of course, is all about electrons. I probably don't need to tell you that. When we talk about reactivity and rearrangements of molecules, we're talking about where the electrons go. And so redox reactions and SN2, SN1 substitution, organic chemistry, it's all about pushing electrons around. And I hate organic chemistry, and so I don't like pushing arrows, but I do have to acknowledge that it is all about electrons and where they go. So that's what chemistry is about. So we want to know where they spend their time, and that tells us a lot about reactivity, physical properties, structure, anything you want to know about chemistry, okay? And so theoretical chemistry is all about using the fundamental laws or equations of nature and physics, along with computational techniques to solve chemical problems. That's what it's all about. So on the left here, we have an example of ethane, which is the molecular structure. So we have carbon and hydrogen atoms. And on the right-hand side, we have an example of what the electronic structure might look like. So this is These are molecular orbitals. This is the sigma bond, or the single bond between the carbon atoms. And then we have a sigma bond or a single bond between the carbon and hydrogen, for instance. So this tells us something about where the electrons are. So from molecular structure, we can calculate electronic structure. So you can calculate nearly anything with computational chemistry. For instance, electronic states. So this is where the electrons are, what they're doing, what energies they have. You can calculate geometries. So on the left is a very badly drawn benzene molecule. And then you can ask the computer to find what the optimal structure, the real structure of benzene is, and it gives you something that looks much more like you would find in a textbook. So you can calculate geometries. You can calculate vibrational energies. So for instance, what energies the molecules and different bonds vibrate at. Reaction barriers, so you can calculate the energy of the reactants, two molecules coming together perhaps. You can calculate the energy of the products when they've done their reaction, and all the energies in between, which allows you to calculate this energy barrier to overcome for this reaction. You can calculate dynamics, so put things in a big box of solvent or a ball of solvent and watch the interactions between the solute and solvent molecules, or look at how things change with pressure or temperature. So you can do all kinds of things. Calculate magnetic properties, and that's what I am particularly interested in, so we'll come back to that a bit later. Absorption spectra, and anything you can think of, really. So anything that you can measure, you can pretty much calculate, is the story. So here's just a very, very brief overview of some of the folks at Manchester Chemistry who do computational or theoretical chemistry. We have a very wide range of interests. I'm not going to go through everything, but for instance, this is looking at how the electrons, where they lie in a neptunium iodine bond, which is quite interesting. So very heavy elements in the periodic table. This is looking at the active site of photosystem 2, which is where you get, which is the oxygen evolving complex in photosynthesis in nature. So this is a very important enzyme, and we don't really understand it, and so you can use computational methods to try and get some more insight. And this is looking at electrostatic potential across larger scale groups. So this is using very different methods, all these three calculations. So you can study length and time scales of very different orders of magnitude, and that's one of the really interesting things about theoretical chemistry. Okay, so why is it useful? Well, you can do a calculation or do some theory to try and understand what your experiment's showing you. So if you measure the infrared spectrum, the vibrational spectrum of a molecule, you might know that, you know, a carbonyl, CO carbonyl bond will vibrate at roughly 1600 wave numbers. But why do we know that? Well, that's from experience. What if you have a very complicated molecule that has lots of peaks all over the place and you have no idea what's going on? Well, you could do a calculation to try and understand what peak is what and what that means. A really topical example is a test before an experiment. So for instance, will a drug molecule bind to a protein? And so this is a picture of a prototypical small drug molecule in the pocket of an enzyme that is important in the pathway of how coronavirus works in the body. So if you can block this site, then coronavirus can't replicate as much. And so this was literally yesterday, and I saw this news article. So it's really, really important to use computational techniques because there is an infinite number of small molecule drugs that you could make. So which one do you want to make to stop coronavirus or you know, treat coronavirus infections? And so it's very, very topical to use computational chemistry to do this kind of experiments. And so before you make it, you test. You could do chemistry that's too expensive or dangerous. So how does radioactive waste interact with steel canisters that you might want to put it in to keep it safe and store it somewhere? Perhaps you don't want to open the lid and look at what's happening. You'd rather do a calculation first. And so you can absolutely do that. Which explosive will have a bigger boom? So you're in a mining company and you want to get the metal out of the rocks over there. Which compound are you going to use? And you don't particularly want to send a poor undergraduate student to make them and then measure it before you know which one's going to blow up. So you can do a calculation and find out which one would be the better one to choose. Or even experiments that cannot be performed in reality. So for instance, in a reaction of two molecules, where do the electrons move first? How does it start? You can't do that in reality, usually. So you can in the computer. You can look at very, very small time steps and see where the electrons are moving. Or it might not be electrons, it might be a proton transfer. And you can distinguish those two mechanisms in the computer. So how does it work? What's the general flow of doing a calculation? Well, first you start with the structure of a molecule. So this might be a guess, this might be from an experiment such as X-ray crystallography, but you guess some kind of structure and you guess what the orbitals are going to be, where are the electrons roughly going to be in this thing. And we know generally how to do that from experience, from many, many years of understanding chemical theory. And so you can automate these guessing processes. For instance, oxygen will have lone pairs. You know roughly where they're going to be. Carbon-hydrogen bonds, you know, carbon likes a tetrahedron, you know that. Or is it sp2? It's a trigonal planar. So we know roughly where the bonds are going to be. And then once you have that first guess, you can calculate the electronic structure, so the states of the electrons and their energies. And from this, you can improve your guess of the molecular orbitals to make it more accurate. And then optionally, you might want to alter your structure a bit to make that more accurate. And then you repeat this, calculate the electronic structure again, and then keep doing this until you find a consistent solution. And this is the way that we find the optimal electronic states and structural configuration of molecules. That is the overall goal of this. And then we can calculate properties. So the central theory is Schrödinger's wave equation. So this is where the quantum mechanics, the bit that I think is fun, but not everyone does, obviously, comes in. And so this is H psi equals E psi is the famous Schrödinger's equation. And H is the, well, okay, so we have two parts to this. The red part is the wave function. So in quantum mechanics, electrons are not just particles, they're waves and particles. So they obey, well, they behave according to a wave function. And that's what the psi in red represents. And the Hamiltonian operator in blue, the H, is just a measurement. And this measures the energy of a wave function. And so this is a very fundamental equation in quantum mechanics. Okay, and so so if we want to understand something about electrons and their properties, we need to solve the Schrödinger equation. And we can write the Hamiltonian, so that's the blue part, we can write that for any molecule. That's actually quite easy. So for instance, for hydrogen, this is what the Hamiltonian looks like. I know it looks scary and it's pretty horrible, but you can actually break it down. So this first part here in brackets, this is the kinetic energy. So we're describing the position of the electron relative to the nucleus of the hydrogen atom with its radius, so r, with theta, which is the angle from any direction, but we're saying z, for instance, the angle in this way, and then phi, which is the angle in the xy plane, okay? And so these are the three coordinates in spherical coordinates, so where is the electron? And this is just describing its motion, its kinetic energy. And then the second part is describing the potential energy, and that's the interaction, the attractive force between the positively charged nucleus and the negatively charged electron. And so that's what we're describing here, which only depends on how far away it is. Okay. So we can write the Hamiltonian, but the hard part is actually getting the wave function. That's the really tricky bit. Now for hydrogen, we can actually write this down exactly. We know exactly what the solution is, and this is it. This is the solution to what the Schrödinger equation for hydrogen. So we have a part that describes something about how far away it is, something about its angles, and then this part talks about the electron spin, which I'm not going to go into too much detail about. So this part in the middle gives you the shapes of the molecular orbital, or sorry, the atomic orbitals that you know. So the 1s orbital is a sphere. The two p orbitals have lobes. That comes from this part here. And so we have our quantum numbers in here. So principal quantum number n, L is your orbital quantum number, and then your magnetic quantum number, and then we have a spin quantum number as well. Okay. So for one electron, it's fine, but for two electrons, there is no exact answer. We cannot solve this equation exactly. Even if we can write the Hamiltonian, there's no way of solving it for the wave function. And so we have to make approximations. And this is where the different varieties of methods of computational or theoretical chemistry come in. And there are so many. And developing new methods is an entire research area that people work in. And so people are experts in some areas and not in others. So I like particular types of approximations, and other people like other ones. So, and some are suitable for some problems and some for others. So it's a very important part of computational or theoretical chemistry, is knowing which tools to use for which problem you're trying to solve. So that's one thing to think about. Okay, so onto my research. Hopefully I don't know how I'm doing for time. We'll be all right. So I work in molecular magnetism, and we start thinking about data storage. Okay, we're talking about magnets. We're looking at how we can improve data storage capabilities. So one thing we know is that the world likes digital data. It turns out to be a very cool thing to watch videos whenever you want and do online conferences and things like this. And this is a very old estimate that the total amount of stored data in the world will be about 44 trillion gigabytes by this year. I think that's hugely underestimated now given the pandemic, but you know, it's a big number. And so we need, ideally, a more compact method of storing all this information. You know, they're using big data centers in the desert at Amazon, Google, Facebook, all of that, not to mention governments. So if we could store this in a more compact way, save a lot of energy, and hopefully make the process a lot cheaper and better for the environment. So the current technology of storing digital information is on hard drives that look something like this. It's still the cheapest and best way of storing lots of information. And the density is about 190 gigabytes per square inch. And that sits on these platters, these spinning platters here. And so if you look at this with a magnetic force microscope, you can see something that might look like this. And so these are different magnetic domains on a hard drive. And so these different patches encode the information. So for instance, this darker patch that's highlighted here could represent a 1, and this lighter patch over here might represent a 0, for instance. So this is the magnetic polarization being either coming out of the plane or out of the screen towards you, and then the other one going into the screen in the other direction. So this is different orientations of the magnetic moment, and this is how we store information in hard drives. So as chemists, we can ask the question, what about molecules? Because they are tiny. Molecules are so small, right? I don't know the statistics about, you know, how many molecules of you know, methane you could put between here and the sun or something, but it's like, you know, far more than the age of the universe, or more than the grains of sand in the universe, or something stupid like that, right? Molecules are so small. The scale is just phenomenal. So if we could use molecules to store information, what would the density be? So this is the first single molecule magnet, which was discovered in the 90s, and it's about 2 nanometers across, or 20 angstroms across. And so let's just call it a square. That would be 2 nanometers squared, which would be, and if we have one molecule representing one binary bit of information, that's 4 square nanometers per bit. That's some tiny amount of inches squared per bit. And if you do the maths, you get about 20,000 gigabytes per square inch, which is about 100 times better than current technology. So if we could store information in molecules, could we shrink data centers by a factor of 100? And so save a lot of energy in the process. That's the aim. So what is this? This is a single molecule magnet, and how does it work? Well, it is a molecule that shows memory effects. That's basically the premise. And the prime experiment we use to show that is a so-called hysteresis experiment. Hysteresis for history. So if we can see a history of the magnetic polarization, also called the magnetization here, then we can show that it has a memory effect. And so this experiment works by, say, applying a magnetic field that is strong in one direction and then sweeping it back towards 0. So we switch off the field and the magnetization stays positive. And if we sweep it in the other direction, we can make it go negative and then pull it back to 0, and it stays negative. And so at 0 magnetic fields, that's with no magnetic field turned on, we can either have the magnetization up or down. And so this 2 configurations in no external magnetic field is the origin of memory. And so we can use it as a 1 or a 0, and that's how we could store information. Now, those of you who have keen vision will see the problem immediately with this proposal is that the temperature scale here in Kelvin is extremely small. So this is a few degrees above absolute 0, which is not very practical if you want to be making a technology to sell to someone. Unless we put it on the moon or something like this, but even that, I think I have this on the next slide, actually. Yeah, here we go. So here's a few temperatures that you might be interested in. So absolute 0 is very cold, and we start about here, and that's not great for selling something. So we ideally want to make this property occur at a higher temperature so we can use it for something interesting. So what do we do in our research? We use lanthanides. And if you watched Dave Mills' talk yesterday, he talked a lot about F elements. So lanthanides sit all the way at the bottom of the periodic table, not quite at the bottom, that's the actinides, but the lanthanides are here. And they have very good magnetic properties, and generally, or simply, that's because at the bottom of the periodic table, you have a lot of electrons. And when you have a lot of electrons, you have lots of magnetism. because it's actually from the spins of the electrons that you get your magnetic moments. So we have lots of electrons, lots of magnetism. Let's use lanthanides. And so how do we make lanthanide molecules? This is possibly a bit oversimplified for any chemists in the audience, but hopefully gets the point across. We can start with an atom, which is neutral. All atoms are neutral, and we can take away some electrons. So in the case of lanthanides, we like taking away 3 negative electrons, which gives us a positively charged ion, or a cation. Okay, and then we can combine this with some ligands or molecules. In this case, these are carbon rings that would like to attach to so negatively charged carbon rings that would like to attach to a positively charged ion. Put them together and we get something that looks like this. And this is a molecule. And it could be positive, neutral, negative, depending on different kinds of things. But in this particular example, it's irrelevant. Okay, so we can make molecules with lanthanides. What molecule shape should we make? You could pick any kind of shape in the world. What would you choose? Well, what we want for a single molecule magnet is to have these two states up and down separated by some energy barrier. So we want there to be an energy cost to flip between these two up and down configurations, so that when we set it in either the up or the down, so this is saying I want that bit over there to be a 1 because that's my grandma's face. I don't want that to be just randomly erased. That's a 1, please. I don't want it to switch to a 0. So we need to make that a very unfavorable process. So we want it to cost energy. So I have to go and change it if I really want to change it. Okay. And so the higher the energy that process costs, ideally, then the higher temperatures we can store memory up to. And that's what we're going to try and do. So what we want to do, though, is make this sideways configuration somehow higher in energy than the up or the down. So when we're switching it, it's got to go through this higher energy state. Okay, so let's break down this particular molecule that I've drawn here, which you'll find isn't arbitrary, but it is chosen for a reason. So let's break this down for a second. So we have this ion that is a lanthanide 3 in the middle. This is made up of a charged cloud of electrons, which are negatively charged. And then in the center, you have a positively charged nucleus. Okay, and on the outside, we've put 2 negatively charged carbon rings. So you will probably know the old adage that opposites attract. Well, this is Coulomb's law of electrostatics. And it also says that like charges will repel each other. So negative charges want to avoid other negative charges. And so if we have this negative charge of negative cloud charge of electrons around the ion, and it's getting very close to these negatively charged rings, well, they're going to want to move out of the way. And so that's what they kind of do in a very sort of loose way. There's a lot more quantum mechanics that goes into this, but you can ask me about that if you're interested. But broadly speaking, the electrons would rather be as far away as they can from these 2 negatively charged rings. And so we can think about it rather being sort of in this configuration rather than pointing in this way. Okay, so this is loosely speaking how we can make this barrier happen. And so the question is, does it work? So this is a molecule that Conrad Goodwin, who was a postdoctoral research fellow in Dave Mills's lab a few years ago, made, and it's this same shape that we've been talking about. It uses the element dysprosium, which is one of the lanthanides, one of the most magnetic lanthanides. And short answer is yes, it does work, quite remarkably so, in fact. So this is the magnetic hysteresis measurement, and we can show that at low temperatures, we have this nice possibility of having an up or a down. So this purple line goes around all the way around the outside there. So at 0 field, we can have an up or a down. And that stays the same, that we can have this open loop all the way up to 30 Kelvin, and actually, if you look closely enough, up to 60 Kelvin. So it turns out we can store information up to 60 Kelvin in this kind of molecule, which is very remarkable because at the time, I think the record was about 14 Kelvin. So we made quite a big jump from where the record was probably somewhere about here at the time, and we jumped all the way up to there, which is really nice because now we're starting to get close to liquid nitrogen. And liquid nitrogen is, well, the atmosphere is 70% nitrogen. And so if you compress that, you've got a very cheap cooling source. And so if we can get molecular data storage above that, then that would be starting to be interesting. Of course, there's a long way to go before anyone's going to have it on, in a warehouse somewhere, but still, progress is progress. And so when we say it needs energy to jump the barrier, what does that mean? Well, we have this barrier here. So energy is loosely associated with movement, okay? If you have lots of energy, you're gonna run around like crazy. And so if you have energy, it's movement. And in terms of molecules, the molecular energy we're talking about is all about vibrations. So molecules move by vibrating, that's how they have energy. And so the microscopic origin of temperature is actually vibrations. So the reason your hand hurts when you touch a hot bar of metal is because it's vibrating a lot, and it transfers a lot of vibrational heat energy to your hand, and then the cells in your hand start going like crazy, and then they start tearing apart and breaking bonds because they're vibrating too much. Basically, that's kind of what happens. More complicated, but yeah. So vibrations. And so we can use computational and theoretical techniques to calculate this in these molecules. So what we do is we take the geometry of this molecule from the crystal structure, and we optimize the geometry in the computer and calculate all the vibrational modes. How can it move? Okay, in vibrating, when it's got some temperature, how can it move? And then we calculate their energies and compare those to the experiment and say, okay, are we good? Are we bad? Are we close? And we're pretty close, so that's good. And then gets the tricky parts, and if you have questions, please ask. We calculate how the electrons interact with all the vibrations, and it uses a different type of calculation. And from this, we can calculate the transition rates between all the different places the electrons can be. So this is a complicated equation. I'm not going to go into it too much, but it has different parts, and we can calculate those with different methods. And once we have all of that information, we can calculate the dynamics. And so that is how the electrons change when the molecule is vibrating. And that allows us to say something about how high the energy barrier is. And so in this particular molecule, it comes out like this. So these red lines are what we've taken a lot of time to try and calculate. And it tells us that the molecule wants to jump up to a very, very high energy state before it can come back down the other side. So on the left, we might have the up, and on the right, you might have the down. And so this is the barrier that we're talking about. And so the real question in terms of chemistry is, which vibrations are important? Because if we can know that, can we change it and get rid of them so that the molecule can't do that anymore? It has to do something else, and maybe that makes it even better. It's these ones. So in this particular molecule, there are a few vibrational modes, and these are two of them that are important. And what we can see is that its motion of these 5-membered carbon rings at the positions where there are no other carbons attached to them. So it's mainly these unsubstituted CH bonds. So the point of our paper here, the conclusion was, wow, okay, so can we just change these? Can we make it heavier? Put a methyl group or fluorine or something bigger than hydrogen, and make this higher energy, slower process so that it's not going to happen anymore. And that's precisely what other research groups have done since. So this is work from a group in Berkeley in the US, and they've made a bunch of different similar rings where they put different substituents on, and they've made the memory temperature go up to higher temperatures. So we were about 60, and they've gone up to 72 in this case here. And these are all getting rid of, on these last three, getting rid of the carbon-hydrogen bonds. Whereas on the left, they've still got a single carbon-hydrogen bond on each ring, and it's actually worse. And then another group following up work from the University of Sussex have done a different type of complex. So now I've got two different rings. They're not the same top and below, but they can show memory up to 80 Kelvin. So that's even further than we've got, and even better than the temperature of liquid nitrogen. So here's your up and your down at zero field, for instance. And so here we are at the current best record holder from a couple of years ago. So this has all happened in a very short timescale, a few years from down here. So we're hoping that we can keep making advances and push this up even higher. So that's all I have to tell you about today in my research. Thank you very much for spending the time to listen, and I'll happily answer any questions that you have.
Thank you, Dr. Chilton, for that talk on theoretical chemistry of magnets. So some of the questions we've got in chat are, what would happen if the ligands consist of a metal, for example, a Keggin anion, for example, a diabatic molybdenum, or why is SMM magnetic hysteresis generally lower for these polyoxometallic complexes?
Okay, so I think that's a question from Takula following up from a Twitter post yesterday. So there's a complicated relationship between the geometry of a molecule and, let's say, the energy barrier. So usually you would say that symmetry is good. So if you have a very high symmetry, so for instance, if you had, let's say, a linear geometry of just two atoms and a dysprosium in the middle, that has very high symmetry, and that's generally good. In the case of big, bulky things, it gets a bit harder. But in the case of these polyoxometallate Keggin anions, They're very big and they hold the dysprosium at a very small point in there. But what they don't do is generate a very strong, what we call crystal field interaction, which is where the charges on these, so if we go back to here, you want to make this happen basically. And what the Kagan anions do is move the charges away from the middle basically. And what that means is you don't get this sort of squishing of the electron density at the dysprosium, but rather it's they sort of wrap around. It doesn't know what to do. And so it's a bit confused basically. And so the energy levels are not well placed. So it's a complicated relationship, but we know why.
Okay, cool. So I've got another question from Eleanor Wright, who wants to know, where do you see your research going next, or what do you hope to achieve?
So we're interested in trying to obviously make or find the reasons or recipes for making better molecular magnets. But more generally, we're interested in how vibrations interact with molecules. So we're looking at how you can make better magnetic resonance imaging contrast agents, so that when you go to a hospital, you can get more information out than just, oh, there's a tumor in your brain there, but you can learn something about the chemistry, and we can do that with knowing the interaction of vibrations in magnetic states. Looking at quantum computing with molecules, which is very interesting and is promising. But again, vibrations are a problem. So how do we stop them from killing the quantum coherence? And also looking at how the energy transfer happens in optical excited states. And this is very important for things like photosynthesis. So where you get the absorption of light, it excites some electrons, but then that energy is moved from this place along a long chain of biological molecules to somewhere else where it does something. It does some chemistry, and that's how you store, that's how the body makes energy, or also how plants make energy in photosynthesis. And so that would be very useful if we could understand how that energy transfer path works. And that's all to do with vibrations, and it's incredibly complicated, but yeah, we're interested in that as well.
Okay. Another question that we got was, can the behavior of a new unknown molecule still be accurately modeled?
Yeah, so this is a cool thing. So all you need to do calculations on molecular properties is an idea, the structure of a molecule. The laws of quantum mechanics don't care. You know, it would even be able to tell you if an unknown molecule was possible to make or not. You can ask the computer, is this molecule stable? And if the answer is no, well, then there's two answers. Either you'll never make it because it will never happen in the first place, or two, yes, but it's only so little, only stable for a tiny little bit, and then it will just explode, basically. So you can certainly do that, yeah.
Okay, cool. The next question was, how redundant have popular theories like MOT become today, and how precisely can we predict the area probability of electrons using the E Schrödinger equation?
Sorry, I missed the start of that question. I'm not sure I quite got it.
How redundant have popular theories like MOT become today, and how precisely can we predict the area probability of electrons using the Schrödinger equation?
So I don't know the first MOC. I don't quite
MOT,
know.
MOT.
MOT is in Ministry of Transport for your car? Sorry,
molecular orbital theory, yeah.
Okay. So how reliable is it? Yeah, it's a good question, because so at the end of the day, quantum mechanics actually doesn't tell you how to build a wave function. I go back to the start here. Building this thing there's an infinite number of ways you can do it. And we use molecular orbitals as a good approximation because we know how quantum mechanics works for atoms, generally speaking, and atomic orbitals seem real. And so if you build up molecular orbitals from atomic orbitals, it's a logical way to do things. It's not the only way. You can build wave functions of electrons in molecules using what's called plane waves, which is basically a wave that's going across some part of space that has some frequency. And you can build that with low frequency waves and high frequency waves. And it doesn't matter. It's just a different method of doing it. You get sort of less intuitive information as a chemist, but physicists, for example, love doing this. But at the end of the day, it doesn't matter. If you do a good enough calculation, so a good quality atomic orbital, molecular orbital thing, or a good quality plane wave calculation, they should give equivalent results. And at the limit of using an infinitely large basis, that is how many different orbitals or plane waves you use, they will give exactly the same results.
Okay, cool. The next question is, how does hysteresis form the basis of magnetic data storage devices? And how good would be the complexes exhibiting electron transfer for storage devices?
So I didn't quite get the second bit, the first bit about hysteresis. So the idea is that once you set the magnetic moment of the molecule, whether that's an up or a down, it stays that way for some long length of time. I mean, of course, even the hard drives in your computer, given the age of the universe, will degrade. They will not be the same. And that's from random events and, you know, cosmic rays or whatever it is. Something will change. It will flip your bits. Basically, they stay for a long time. And so that's the basis of this experiment. So of course, for strong magnetic materials in hard drives, in wind turbines, in electric motors, things like this, permanent magnets, they have big hysteresis at room temperature. So, you know, once you set it, it stays that way. It's the same with your fridge magnet, right? Your fridge magnets will be pretty useful if they kept on falling off. So this is one of the observable properties of magnetic materials. And the second part I didn't quite understand.
So it says, how would you program them so they can be used for storage without changing the molecules next to them?
How would you program them? That's a really interesting one. That's one of the tough challenges that as a community we haven't really addressed yet. So you would have to say, first of all, fix them in space somehow. So that could be, you know, two-dimensional array, like we think about you know, conventional hard drives. We think about having a disk platter that has domains on it. So you could think about having a surface and putting molecules on it and then changing each one by one. That's difficult because you have to localize a magnetic field on the scale of a few nanometers. And the technology for doing that is not exist, I would say. You could also use things like maybe a scanning tunneling microscope where you have a very sharp, atomically sharp tip, and you go over a molecule, you can maybe pass some charge through it, and you can use charge to switch magnetic states as well. So that's one possibility. Or you can think about a three-dimensional array where you might have an ordered crystal in 3 dimensions of this material, and how you would address that locally. I don't know, you have to think about beyond diffraction limited optical methods, but there might be a way that you can think about doing that in the future, yeah.
Could you throw some light on the economics of molecular magnets? Sorry, that's my dog barking in the background.
Economics. There's not really any economics to discuss at this point because no one's made a device that actually uses them. So we're so far away from that. This is very basic research, and what we're learning is how to control the geometry of molecules to control electronic and magnetic states. And that's something that people have been struggling to do for 30 years, and we now know what shapes we need to make. Now we're learning how to design the vibrational states of molecules to make this better. And so once we know both of those things, hopefully we can start moving forward. But yeah, at this stage, no one's made a device, so the economics are not known. I mean, the cooling requirements now would be worse than the existing technologies, for instance, if they could be made.
Okay. Another question we got was, what kind of group projects can third and fourth year students expect if they choose this physical chemistry for their projects?
So, well, at Manchester, our teaching sections are in IOP, so inorganic, organic, and physical. Computational sort of straddles all of them, or theoretical straddles all of them, and so projects are offered in different areas. So for instance, I teach in the inorganic and the physical section, but some of my colleagues do very organic type theoretical chemistry. So it really depends on what who you want to work with or who you're looking at. So there are projects across sort of drug discovery, enzyme kinetics, magnetism, bonding in heavy elements, yeah, anything you can think of really.
Okay. So someone's asked, is there someone start learning computational chemistry? Is there any online research trying theoretical chemistry that you could recommend?
There are lots of really good books, obviously, and most sort of computer programs that do these calculations have tutorials, and there are a number of freeware packages. So for instance, Orca is a freeware DFT, density functional theory program that is very good, that we use in research. There are many codes. I mean, there's so many, but all of these will have little tutorials about, okay, how do you optimize the geometry of methane, and how do you find the bond length, how do you find the vibrations, and things like this. So the tutorials are a good place to start, because you can just get in and do it yourself, and try it until it breaks, and then do some of your own research, basically. In terms of the theory, there are, if you just Google, computational chemistry and wave functions or approximations and things like this, you'll get a lot of information. Books are generally good because they take you through step by step what's there, and the university library has lots of good resources there.
Okay, cool. Next question is, what is the most efficient model to calculate the energies of f orbitals for dinuclear lanthanide-based single molecule magnets?
Oh, that jumps in the deep end. Dinuclear, so this is where you have two metals, two F elements. They're hard, and so so I mentioned different techniques and approximations. The thing about lanthanides is that you have, I don't know if I've even got a picture that's going to do this. You have lots of different energy states. So all of these different black lines is a different state the electrons can be in, and many of the approximations in theoretical chemistry only allow you to look at one of these. So for instance, you could only look at this one, and that would be irrelevant. It would be useless if you wanted to do this kind of information, get this kind of information. So you need to use an approximation method that allows you to get all of them. And there are only a few kinds of theories that let you do that. And the problem is they're very, very expensive to run. Not money-wise, but time-wise. And so that gets even worse when you have more than one metal, and it scales exponentially. So, well, actually, it scales worse than exponentially. It scales factorially. So, it's possible, but it's just really hard. And there are lots of questions over how F elements communicate with each other, so how they interact magnetically, and that's not well known, I would say, or well understood, even from a basic theory perspective. So that complicates things, and it's possible that the approximations you use are not good enough to actually get those interactions very well. So there are lots of levels to doing complicated materials like this.
Okay, yeah. This next question is not really chemistry related, but I'll ask it for the sake of inclusion. If you could play any character from a musical, who would it be?
Oh, so I haven't really kept up with more current musicals. That's a good question though. I would have to. I really enjoyed. I did a production of Footloose many years ago, and I really enjoyed that. I wasn't playing the lead, but the lead character in Ren in that show is really cool. So that's the Kevin Bacon part in the movie. Yeah, that's a nice one.
Okay. Back to the chemistry. Does the Hamiltonian operator of hydrogen or any other element change when it ionizes?
Well, if you ionize hydrogen, you don't have an electron, so you no longer have an electronic equation. That doesn't mean that quantum mechanics doesn't apply. It just means that the usual stuff everything I've talked about here is about electrons. So the nucleus has its own Hamiltonian basically, and we usually ignore that because it's the time scale. So electrons move very fast; they have a lot of energy. So we can separate the nuclear part from the electronic part and do the electrons, and that's fine. And just consider the nuclei as sitting there and not moving. If you get rid of the hydrogen electron, then you've just got the nucleus. So you must do the nuclear equations. But if you're talking about general molecules, so if you have helium, say, and then you ionize helium, and you only have one electron, we have now what's called a hydrogenic-like ion. So helium plus looks a lot like hydrogen, except it's got an extra proton. And so you can just change this equation. So this equation will still work. All you have to change is this part here, which is the interaction. Now you've got two positive charges versus one. So the interaction's a little bit different, but the equation's still valid. You get different solutions. And the Hamiltonians, you just adapt based on the electrons you have.
Okay, so the next question is, do you think that SMMs will be viable in terms of cost and environmental impact at some point?
Who knows? The future's a long time. Within my lifetime, probably not in a commercial technology. I think if we can manage, you know, in the next 20 or so years to make a demonstrable storage device in the lab that uses molecular magnets, that would be excellent progress. And then beyond that, who knows whether economics of scale will work or some other technology will come in and beat it far, far beyond, and off we go. We don't need it anymore. Who knows? Okay.
The next question is, so being a chemist yourself who has already developed software such as PHI and CC Fit2 relevant to molecular magnetism at such a young age, what advice would you likely give to a student who is interested in the field of quantum mechanics and computational chemistry?
What advice? If you're interested in it, just do it, and don't try and. So one thing that pop science people say a lot, you don't hear so many academics say it, but everyone is a researcher. You can just go and download a computational chemistry program and do some calculations. You don't need permission. You don't need expert training. You know, you can learn as you go. I taught myself how to do a lot of things, and you can do that too. There's nothing stopping that. And along the way, you know, find mentors or people who can help train you in certain ways. So, you know, if you want to do a master's project in that area, great, PhD, so on and so forth. Learn new skills as you go, but just do it and learn. And if you want to ask questions, just ask questions. Send me an email. Send anyone out there an email. And if they don't get back to you, then that's not a person you want to speak to, because clearly they don't have the time or they don't care. But people who, you know, find people who will help you and are interested in helping you, and then learn. And yeah, when you're interested in something, that's where you're going to be the most creative and the most productive and have the most fun. And that's what it's all about, you know, learning. I'm always learning, and I make stupid suggestions that my students will try, and they'll either prove me wrong or I'll be right. And then whatever way it goes, we'll learn something. And that's what research is. So just do it is my best piece of advice.
Okay, only 2 more questions left. Oh wait, 3. If the SMS was placed in a field of another magnet, how susceptible would it be to damage? Would the data be erased?
Oh, good question. So when you apply a magnetic field, you can change the magnetic polarization of anything. So in a single molecule magnet, you only need, well, it depends on which material you have, but usually you don't need very large magnetic fields to do that. Now that's on one hand a good thing, because you want to have only a small magnetic field needed to switch it, so that you can, when you want to do it, say in a device, you only have to have a very small magnet to say, okay, change. You don't want to have to apply a massive magnetic field, and you know, that's difficult. So that, on one hand, that's good. But as you say, on the other hand, if you accidentally dropped a magnet near your single molecule magnet storage device, would you destroy everything? And so you need to protect against that as well. So any magnet is susceptible to being erased by another one. You just need to know the limits and how to protect them in a safe way. And that would all be part of designing a device, which, as I've said, we have not got there yet.
Okay. What would happen to the data stored when the material relaxes to its initial state?
So relaxation is, the community uses this term, and what we mean is, what we're talking about is when it flips, it relaxes between the two states. But that, if you're switched on, that actually isn't right. There's nothing to do with relaxation. These two states are the same energy. There's no relaxing happening. And so what we actually mean is that if you take an ensemble, lots and lots of molecules, and you put them in a magnetic field, most of them will go spin. Say you put a magnetic field in this direction, they'll all put their magnetic moments up. That is, and then if you take off the field, you still have them all pointing up. That is, now we're in zero field, but we have everything pointing up. That is a very out of equilibrium situation. So equilibrium, everything should be random. So they should be 50% ups and 50% downs in some random distribution. That's equilibrium in zero field. So this all aligned case has a very, very low entropy, and that's not how nature is. And so what we mean by relaxation is that when some of them start flipping, And so some of them are just going over the barrier, and the overall sample is returning to equilibrium. It's relaxing back from this out of equilibrium situation to the equilibrium. So that's what we mean.
Okay, I think that's all we've got time for. So to wrap up, I want to say a big thank you on behalf of KenSoc and the PASS and everyone in this chat for the talk, Dr. Chilton, for your time, obviously, everyone for coming along. This room will be closed shortly, but if you've got any more questions, I'm sure you can email Dr. Chilton and he'll be happy to answer them. And finally, there's a little competition that we're doing on behalf of KenSoc and PASS that about submitting a piece of work summarising each talk. And whoever has the best talk, we will give a certificate out to, and it'll look
Fantastic.
Yeah, look for more information on the recorded talk on KenSoc and PASS social media accounts. And thank you everyone for attending.
Thanks everyone. Have a nice one.
Take care. Bye.